In the name of Almighty God, I am Master Sankoshi, and today I want to talk about lemon battery. A lemon battery is a simple battery often made for purpose of education. Typically, a piece of zinc metal such as galvanized nail and piece of copper such as penny are inserted into a lemon and connected by wires. Power generated by reaction of the metal is used to power a small device such as a light-emitting diode or LED. The lemon battery is similar to the first electrical battery invented in 18th century by Alessandro Volta, who used brine or salt water instead of lemon juice. The lemon battery illustrates the type of chemical reaction oxidation-reduction that happens in batteries. The zinc and copper are the electrodes, and the juice inside the lemon is the electrolyte. There are many variations of lemon cell that use different fluids or liquids as electrolytes and metals other than zinc and copper as electrodes. And what about the use in the school project? There are numerous set of instructions for making lemon batteries and for obtaining components such as light emitting diodes or LEDs, electrical meters or multimeters, and zinc coated or galvanized nails and screws. Commercial potato clock science kits include electrodes and a low voltage digital clock. After one cell is assembled, a multimeter can be used to measure the voltage or the electric current from the voltaic cell. A typical voltage is 0.9 volt, with lemons current are more variable but range up to about 1 milliampere. The larger the electrode surfaces, the bigger the current. For a more visible effect, lemon cells can be connected in series to power an LED or other devices. The series connection increases the voltage available to devices. Scientists have published a list of low voltage devices along with the corresponding number of lemon cells that were needed to power them. They included LEDs, piezoelectric buzzers, and small digit clocks. With the zinc copper electrodes, uh, at least two lemon cells were needed for any of these devices. Substituting a magnesium electrode for the zinc electrode makes a cell with a larger voltage between 1.4 to 1.6 volt, and a single magnesium copper cell will power some devices. Note that incandescent light bulbs from flashlights are not used because the lemon battery is not designed to produce enough electric current to light them. Such a battery typically produces 0.001 ampere or 1 milliampere of current at a potential difference of zero point 0.7 volt. These values are multiplied together to determine the overall power of 0.007 watt or zero point 0.7 milliwatt. And what are the variations? Many fluids and liquids can be used for the acidic electrolyte. Fluid is convenient because it provides both the electrolyte and a simple way to support the electrodes. The acid involved in citric fruits such as lemons, oranges, grapefruits, and etc. is citric acid. The acidity, which is indicated by the measured pH, varies substantially. Potatoes have phosphoric acid and work well. They are the basic for commercial potato clock. Potato batteries with LED lighting have been proposed for use in poor countries or by off-grid populations. International research begun in 2010 showed that boiling potatoes for 8 minutes improves their electrical output, as does placing slices of potato between multiple copper and zinc plates. Boiled and chopped plantain pit or steam is also suitable, according to Sri Lanka researchers. Instead of fruit, liquid in various containers can be used. Household vinegar containing acetic acid works well, and researcher was featured in one episode of the US television program Head Brush, an offshoot of the Miss Boosters program. The researcher had been canned and became the electrolyte, while the can itself was one of the electrodes. Zinc and copper electrodes are reasonably safe and easy to obtain. Other metals such as lead, iron, magnesium, and etc. can be studied as well. They yield different voltage than the zinc copper pair. In particular, magnesium copper electrodes can generate voltage as large as 1.6 volt in 11 cells. This voltage is larger than obtainable using zinc copper cells. It is comparable to that of the standard household batteries 1.5 volt, which is useful in powering devices with a single cell instead of using cell in series. And what about the learning outcomes? For the youngest pupil, about age 5 to 9, the educational goal is utilitarian. Batteries are devices that can power other devices as long as they are connected by a conductive material. Batteries are components in electrical circuits. Hooking a single wire between a battery and a bulb will not power the bulb. For children in the age range between 10 and 13, batteries are used to illustrate the connection between chemistry and electricity as well as to deepen the circuit concept for electricity. The fact that different chemical elements such as copper and zinc are used can be placed in the larger context that the elements don't disappear or break down when they undergo chemical reactions. For older pupils and for college students, batteries serve to illustrate the principles of oxidation-reduction reactions. Students can discover that two identical electrodes yield no voltage and that different pairs of metal beyond copper and zinc yield different voltage. The voltage can and current from series and parallel combinations of the batteries can be examined. The current that is output by the battery through a meter will depend on the size of the electrodes, how far the electrodes are inserted into the fluid, and how close to each other the electrodes are placed. The voltage is fairly independent of these details of the electrodes. And what about the chemistry? Most textbooks present the following model for the chemical reaction of a lemon battery. When the cell is providing an electric current through an external circuit, the metallic zinc at the surface of the zinc electrode is dissolving into the solution. Zinc atoms dissolve into the liquid electrolyte as electrically charged ions, leaving two negatively charged electrons behind in the metal, which means the equation of Zn goes to the Zn2 plus 2 electron negative. This reaction is called oxidation. While zinc is entering the electrolyte, two positively charged hydrogen ions or H plus from the electrolyte combine with two electrons at the copper electrode surface and form an uncharged hydrogen molecule or H2. This reaction is called reduction. The electrons used in the copper to form the molecules of hydrogen are transferred from the zinc through an external wire connecting between the copper and the zinc. The hydrogen molecules formed on the surface of the copper by the reduction reaction ultimately bubble away as hydrogen gas. The experiment results. This model of the chemical reactions makes several predictions that were examined in experiments published by Goodisman in 2001. He notes that numerous recent other purpose chemical reactions for the lemon battery that involve the dissolution of the copper electrode into the electrolyte. He excludes this reaction as being inconsistent with the experiments and notes that the correct chemistry, which involves the evolution of hydrogen at the copper electrode but also can use silver instead of copper, has been known for many years. Most of the detailed predictions of the model apply to the battery's voltage that is measured directly by a meter at open circuit. Nothing else is connected to the battery. When the electrolyte was modified by adding zinc sulfate or ZnSO4, the voltage from the cell was reduced as predicted using the Nernst equation for the model. The Nernst equation essentially says how much the voltage drops as more zinc sulfide is added. The addition of copper sulfide or CuSO4 didn't affect the voltage. This result is consistent with the fact that copper atoms from the electrode are not involved in the chemical reaction model for the cell. When the battery is hooked up to an external circuit and a significant electric current is flowing, the zinc electrode loses mass as predicted by the zinc oxidation reaction above. Similarly, hydrogen gas evolves as bubbles from the copper electrode. Finally, the voltage from the cell depends upon the acidity of the electrolyte as measured by its pH. Decreasingly acidity and increasingly pH causes the voltage to fall. This effect is also predicted by the Nernst equation. The particular acid that was used, citric, hydrochloric, sulfuric, and etc. Doesn't affect that voltage except through the pH value. The Nernst equation prediction failed for strongly acid electrolytes or pH is less than 3.4. When the zinc electrode dissolves into the electrolyte, even when the battery is not providing any current circuit. The two oxidation-reduction reactions listed above only happen when electrical charge can be transported through the external circuit. The additional open-circuit reaction can be observed by the formation of bubbles at the zinc electrode under open circuit. This effect ultimately limited the voltage of the cells to 1.0 volts near room temperature at the highest levels of acidity. And what about the energy source? The energy comes from the chemical change in the zinc when it dissolves into the acid. The energy doesn't come from the lemon or potato. The zinc is oxidized inside the lemon, enhancing some of its electrons with the acid in order to reach a lower energy state, and the energy release provides the power. In the current practice, zinc is produced by the electrowinning of zinc sulfide or called reduction of zinc with carbon, which requires an energy input. The energy produced the lemon battery comes from reversing this reaction, recovering some of the energy input during the zinc production. And what is about the Smith cell? From the 1840 to the late 19th century, large voltaic cells using a zinc electrode and a sulfuric acid electrolyte were widely used in the printing industry, while copper electrodes like these in lemon batteries were sometimes used. In 1840, Alfred Smith invented a refined version of this cell that used silver with a rough platinum coating instead of copper electrode. Hydrogen gas clinging to the surface of a silver or copper electrode reduces the electric current that can be drawn from a cell. The phenomenon is called polarization. The roughened platinized surface speeds up to the bubbling of the hydrogen gas and increases the current from the cell. Unlike the zinc electrode, the copper or platinum silver electrodes are not consumed by using the battery, and the details of this electrode don't affect the cell's voltage. The Smith cell was convenient for electrode typing, which produced copper plates for later press printing of newspapers and books, and also statues and other metallic objects. The Smith cells used amalgamated zinc instead of pure zinc. The surface of this sort of zinc has been treated with mercury. Apparently, this sort of zinc was less prone to degradation by an acidic solution than is pure zinc. This sort of zinc and placing electrodes give essentially the same voltage when the zinc is pure. With the imperfectly refined zinc in 19th century laboratories, they typically gave different voltage. In popular culture, this section needs additional citation for verification. Please, unsorted material may be challenged and removed. In this video game Portal 2, list of battery types. This is a summary of electric battery types composed of one or more electrochemical cells. Two lists are provided in the table. The primary non-rechargeable and the secondary rechargeable cell lists are listed of battery chemistry. The third list is a list of battery applications. Batteries by applications. The first one is automotive battery. Next is backup battery, battery vacuum tube, battery pack, battery room, battery storage power station, BU battery, button cell, CMOS battery, common battery, commodity cell, electric vehicle battery, flow battery, home energy storage, inverter battery, lantern battery, nano batteries, nanowire battery, local battery, and polar pulse battery, photo flash battery or reserve battery, a smart battery system, and watch battery, watch activated battery. And what about electrochemical cell? An electrochemical cell is a device that either generates electrical energy from the chemical reactions into a so-called galvanic or voltaic cell, or induces chemical reactions, electrolysis, by applying external electrical energy in an electrolytic cell. Both galvanic and electrolytic cells can be thought of as having two half cells consisting of separate oxidation and reduction reactions. When one or more electrochemical cells are connected in parallel or series, they make a battery. Primary battery consists of single-use galvanic cells. Rechargeable batteries are built from secondary cells that use reversible reactions and can operate as galvanic cells while providing energy, or electrolyte cells while charging. Thank you so much for watching my video until the end. Also, you can download this simulation from my github.com/masterscript. As you can see, I have used a physical module as a tertiary current distribution Nernst Planck, and you can see that how it's a species charge. And what about the pellet for voltage and current, power, electrolyte potential, and etc.